Hi all, Klingberg here. Today I thought I'd share with you what I believe to be the final round of ground tests for my wing. I believe I've solved all of the controllability issues on the wing, and this was a round of ground testing to prove out that the flow conditions on the wing are as I expected and desired. I've managed, with the change in the Elevons, I've managed to achieve much more attached flow, and especially out at the wingtip, which is really important. Minimized the spanwise flow and greatly increased the area of the Elevons, which will give me more control authority. I believe that I've more than doubled my roll rate, and the pitch capability seems to still be fine. Reduced the throws a little bit on pitch, and everything seems peachy. So what we tested here at Pacifica the other day was just the left wing panel, the main wing panel, the winglet, and the wingtip panel. As you can see here, I extended the Elevons along the same hinge line of the inboard Elevon. I've extended those all the way out to the wingtip, and you can see that seam in the shot from the top of the winglet. We're going to be particularly interested in looking at the tufts and the flow conditions as I deflect the Elevon. Please ignore the two rows of tufts that are closest to the winglet, because the flow around those is being disturbed by the tool bag, which is sitting on the wing to keep it from flying away. The wind was blowing around 10 to 15 miles an hour, and when I deflect the Elevon down, there's quite a bit of lift on the wing, and it had a tendency to lift up. Holding the other end is my buddy Daryl, who came out to give me a hand with the tests, and a shout out to Daryl. Thank you very much for that help. It wouldn't be possible to do this project without help from my friends. So we're going to be particularly interested in maximum deflections up and down, and this Elevon is set up so that it can achieve 30 degrees of motion in both the positive and negative directions. And we know from previous tests that flow separation started occurring around 15 or 17 degrees of deflection, and you will see cases here where the flow is still attached at the tip at up to 30 degrees of deflection. So it's quite an improvement, and I really believe that's a result of the having the hinge line close to the maximum thickness point of the wing, which means that the flow has maximum velocity and hence maximum momentum, so that it can either make it up the Elevon or around the corner and back down. And it all seems to be working out quite well. So without further ado, let's take a look at the video. Okay, here we go. I've slowed this video down a little bit so that I have time to speak over the top of it. You see me getting ready here. I have an inclinometer connected to the trailing edge of the Elevon here, so I can tell what angle I'm deflected at. Here we're going to 30 degrees up Elevon, and you'll note that all of the tufts look nicely attached. Nobody's trying to slide out spanwise. Of course, ignoring those inboard rows of tufts that are blanked by the toolkit. So all of the flow there looks excellent. Might have a little bit of spanwise flow near the tip, but compared to other situations I've seen, this is really excellent flow. It looks really good. And inboard, we see on the inboard Elevon, we see the same type of conditions. Two rows of tufts are disturbed by the toolkit, but the rest of them are sitting there nice and straight and go right up over the Elevon like we want them to. So the flow is staying well attached and not doing anything really weird. So it's great. And in a moment here, I'm going to deflect it down, and this will happen pretty quick, and we get a little bit of spanwise flow at the trailing edge, towards the trailing edge. And then we see it separate there. The wind kind of died. It went down really low, like 8 miles an hour. It's really not a fair test. So then we waited for the wind to pick up, just waiting for a little bit here. And then we're going to take a look at deflecting it downward again. What you'll see is the slightly inboard tufts will begin to go spanwise, but the ones out at the tip stay straight. And that's that high speed flow coming from the maximum thickness point of the airfoil, going over the Elevon and around the corner, and down she goes, and everybody's well behaved. So there you see the inboard two tufts are pointing outboard, towards the tip, but the two tufts out at the tip are nice and straight. So that's what we like to see. We got a little bit of separated flow there, which I wish I didn't have, but can't be avoided in this particular configuration. And there, the tuft next to the most outboard one went a little bit spanwise, but the last row of tufts stay attached, well behaved. My hand might be disturbing them slightly, but overall the flow looks pretty good. At all times, at least half of the Elevon, the flow is nicely attached and doing its job, and that's at very extreme deflections. 30 degrees is a very large deflection on any control surface. So pretty darn good results, especially compared to what I had in the past, which was only 15 to 17 degrees of deflection before it all separated. Inboard, we're still getting some pretty good behavior there. The tufts are going a little bit spanwise, might be showing a little bit of separation, but overall better behaved than they were in the past, and that's probably due to the change in the potential flow field by having the additional Elevon outboard. That'd be my initial guess why the flow is much better behaved now. So overall, a huge improvement. You'll see a little wiggling around of the picture here, and that's because the camera's mounted on the tip of the winglet, which is pivoting on its yaw tube. So sorry about that. I should have locked it in place, but we'll live with it. It's just an engineering test. We're not here for pretty and fancy. So we went through a series of these. Had to wait for the wind a little bit. Wasn't quite as windy as it was supposed to be, and we did a series of deflections to prove that the data was consistent and the way that I wanted it. And it just all, to me right now, it all looks really good. So I've made some final changes and upgrades to some other components of the glider, and everything is pretty much ready to go for more flight testing. I think the flight test, the next series of flight tests will be at El Mirage, and we'll do them as towing tests. We'll rerun the series I ran before. Here's another downward deflection. You see the flow is reasonably organized out at the tip. We got a couple of tufts disagreeing on which way to go, but at the very tip, they're well aligned and behaved. Certainly way better than we've seen in the past. So overall, big improvements. Okay, for this final segment of the video, Daryl and I actually lifted the wing up off of the sawhorses so we could get out of some of the turbulence near the ground into smoother air at a higher speed, and it worked fairly well. But every time I moved the Elevon, of course, we put interesting loads on the wing, and we had to fight against the wing trying to fly away from us and pitch up or pitch down. It was a little bit of a struggle, but I think we got some good results that way. And not quite, we're at Pacifica here. It's not quite as nice as the sand dunes in Marina Beach. A lot of turbulence in rotary areas. In fact, we spent a good hour in the morning finding the perfect spot to do this. And I think this one worked out reasonably well. We got good. Okay, here we go. And once again, I have this video slowed down slightly so I can speak over the top of it. There initially it got a little too high angle of attack, and we actually stalled the wing. And you saw that real quick there. The tufts up front went a little wild. Now, without the toolkit sitting on it, you can see what the flow is doing near the winglet mount. There we're seeing a big downward deflection. We're seeing some spanwise flow, except the last two rows of tufts, or the last row of tufts on the Elevon, and overall pretty good. There we had a little separation there. I think it's because the wind slowed up. We're seeing that the whole tip is separated at maximum deflection down. Could be angle of attack. That's probably what it is. We're running up a higher angle of attack. We're seeing some spanwise flow inboard. We're getting some spanwise flow outboard. But on occasion, the last row of tufts are still attached and going straight. Upward deflection, same as the other angles of attack. Really well behaved in this configuration. Everybody's lined up now nice and straight. But overall, in the downward deflection, we're getting a good 20 degrees of deflection without spanwise flow. There's a lower angle of attack, and the flow is still in pretty good shape. Not perfect, but pretty good. If you took just about any other control surface and deflected it that far, you'd see all kinds of separated flow. So it is somewhat dependent upon the angle of attack that the wing is at. If you're up to a high angle of attack and you put in full down elevator, you're going to get some span-wise flow and separation and drag. But that's an unusual circumstance. I can't imagine if you're flying really slow and all of a sudden cram in full down elevator. I don't know, maybe you're doing an outside loop, which would be crazy. You do not want to do something like that in a hang glider. So there we go. I hope you enjoyed the video, and stick with me and be prepared for some exciting flight tests. Fly safe, and bye for now.